In this work, we present the concept of sortedness, which is the level of agreement between two points, often from different spaces, according to how they rank the remaining points as neighbors. Visualization techniques provide useful tools for data exploration and decision-making. If a dataset has up to 2 or 3 attributes or dimensions, scatter plots can be good alternatives for exploring intuitive notions such as spatial distribution, distance, and neighborhood. However, some sort of dimensionality reduction is usually necessary for datasets with more dimensions. For this reason, we explore the scenario of dimensionality reduction. Despite the advances in the field, it's inevitable that the mapping process from a high dimensional to a projected space incurs in loss of information due to the high intrinsic dimensionality of many datasets. Therefore, dimensionality reduction techniques are often subject to a trade-off between interpretability and reliability, raising the question of how to effectively assess the impact of the implicit loss of information. Here, the overall sortedness of layout and also the quality of each transformed point are of interest. Layout interpretation depends on the human intuition, which is strongly biased by spatial concepts like proximity and ordering. This is also the case for many machine learning pipelines and most induction algorithms. Taking decisions or inducing accurate models often require a reliable data transformation at local and global levels. Many measures have been proposed to evaluate the dimensionality reduction quality. Here, we will focus on two widely used measures: stress and trustworthiness. Different projection artifacts are detected in different levels depending on the measure. More on this later. Artifacts exist due to the intrinsic loss of information when making a high-dimensional data interpretable. Current ways of measuring such loss of information have noticeable limitations. The most general measure is critical stress Formula 1. It provides values that cannot be directly compared across datasets with very different dimensionalities, sizes, or attribute types. It's also excessively sensitive to minor data perturbations. This happens because it measures the difference between the distances calculated in the original space and those calculated in the projected space. The stress value ranges from 0 to 1 when normalized. The smaller the value, the higher the quality. Unreasonably good stress values can be observed for very disordered dimensionality reduction results. Another limitation lies in the arbitrary thresholds provided by its author, and is still in use today. Trustworthiness is also widely used. It measures the precision of the low-dimensional neighborhoods regarding false positives. It's less sensitive to minor perturbations, but is limited by its dependence on a parameter, the number of neighbors. Continuity is a similar measure that focuses on the false negatives instead of the false positives. Our proposal is a family of measures based on the concept of sortedness. In the context of dimensionality reduction, sortedness can be interpreted as how well preserved is the dataset structure after a transformation regarding the order of the points. For a given point, it's calculated as the Kendall correlation index between the ranking of the neighbors in the original space and the ranking of the neighbors in the transformed space. This is the most commonly used statistics to understand the correlation between two different scores for the same set of items. Here, all points are included in the ranking, not only the literal neighbors. For this reason, we adopted the weighted Kendall to leverage the importance of the nearest neighbors. The main proposal can be used as a local measure or as a global measure by taking the mean value. It should suffice for most use cases. The focus is on how preserved is the order of neighbors according to the point of interest. Here, the dashed circles indicate where the distorted points should be. In this case, 2 points have swapped their orbital path centered at the point of interest. We consider this as the most drastic distortion. The more distant the neighbors between themselves, the more misleading the projection. Reciprocal sortedness was proposed just for the sake of completeness. It builds the ranking the other way around. It's assigned by the neighbor to the point of interest. Changes in the reciprocal ranking affect the measure. We can see the change on how each neighbor ranks the point of interest. The distance indicated by the red line was the shortest. After the distortion, it became the longest. Its application is an open question right now. It's certainly related to the concept of humbleness. Pairwise sortedness provides a unique value for the entire dataset, which is analogous to the stress measure. It's more sensitive as it also detects changes unrelated to the order in which neighbors appear. We can see that despite the translation of a point, their distances to the point of interest are still the same. Weighted pairwise sortedness is an adaptation of the previous measure to make it a local measure. This variant focuses on the quality of the neighbors of a given point according to how preserved are their pairwise distances. The difference between how our main proposal called sortedness and the weighted pairwise variant weighted rankings is that the former considers the original ranking as an indicator of importance, while the latter weights the ranking according to how close to the point of interest is each pair of points. We sketched a tentative hierarchy of increasingly relevant changes to illustrate how the measures relate to each other. Rigid motion and proportional changes in scale are undetectable by any of the methods, as expected. Minor distortions, that is, changes that keep order, affect the stress value, which is usually not desired. Changes in the ranking of pairwise distances might be relevant for some applications. They affect stress, the global and the weighted proposed measures. Changes in the reciprocal neighborhood ranking affect the previously mentioned measures. In reciprocal sortedness, this measure is not necessarily more sensitive than the pairwise variance. Our main proposal detects only extreme cases of change, for instance, when possibly no adjacent neighbors are swapped. The main advantages of our proposal are: it has a standard interval of values where 1 means perfect sortedness, 0.5 means half of the neighbors are still ordered, always taking the weights into account. 0 means that no relevant information about ordering was preserved, which is equivalent to a random projection, and negative numbers are not usually expected in practice, as they indicate an ordering that begins to match the opposite of the expected. Therefore, values close to -1 are very unlikely to happen, unless if the projection is intentionally designed for this. Additionally, as explained earlier, it's robust to relevant distortions. Parameterization is optional. However, the weighting scheme is mostly necessary. It helps to leverage locality. The hyperbolic function suits well for the intended purpose as shown in the experiments. Their values are meaningful in the sense that all proposed measures fit in the 0-1 interval, as shown in this experiment with 1,000 random points, where we randomize the location of part of the points. 100% randomization led to 0 values, while stress and trustworthiness were unable to show such correspondence. These box plots show the same experiment in more detail. At 50% randomization, the bulk of the points were classified between 0 and 0.5 by our main proposal. The weighted pairwise variant had higher variability under lower randomization levels due to its higher sensitivity. In another experiment, we created a randomized dataset with 3 non-overlapping clusters. We swapped the position of 2 clusters to simulate a global change. In this chart, we have in the x-axis the cluster size. Trustworthiness was unable to detect the change for clusters larger than 5 points, as expected. The stress value was the same for all cluster sizes. The global pairwise variant stabilized around 0.5, well below the other measures as expected, although the localwise measures were still able to detect the global change, showing their applicability for both local and global change detection.